to the 7/3, which really what you have to do is add exponents. Same base as we add exponents. Well, can you add 1/3 and 7/3? I mean, yeah, they've got the same denominator, really, haven't they? You're really just saying 1 plus 7 over 3, which is 8/3, isn't it? And so when I get that, what I've got is, and I'll write it down here, x to the power of 8/3, 8 over 3. Now, there's no fraction involved in this one. I'm going to go ahead and finish it out, because what I want to do is write it as a rational expression, okay? Radical expression. I always say those backwards. And I want to fix that by saying, okay, this is really the cube root, isn't it? It's really the cube root of x to the power of 8. Now, let's finish it. Are there any cube roots that you see inside that exponent of 8? What would you say? I mean, how many? Yeah. So I could, in fact, if we're going back to what we were doing, you could think of it as x to the power of 3 times x to the power of 3 times what's left over, x to the power of 2. Remember, same base as we're multiplying, we add exponents, right? So I can take this one out and it becomes just plain old x. I can take this one out of the radical, it becomes plain old x. And when I say x times x, what I've got is, I'm not adding now, I'm multiplying, right? What I've got is x squared times the cube root of whatever was left over, right? What's left over? Don't forget the index there, the cube root of x squared. That's as simple as it can get. Remember, we're testing on this next week, guys. If this is shaky, you really need to put some work into it, okay? Because this is the last day of lecture, and we review on Wednesday, and you have a test on Monday. Got it? Yeah.
I thought it was like a perfect cube, isn't it? So there wouldn't be any number.
Well, it would be a perfect cube if it was the number 8.
Okay.
But this is an exponent. So what do you do with exponents? Well, you divide them by the index. Well, 8 won't divide by 3, but I do have some 3's inside it, remembering that I add these together when I multiply the basis with the exponents. If that was a number 8, the cube root of it would be 2, if it had a coefficient of 8, okay? I know it's confusing. That's why you have to put a lot of practice into these problems. All right, let's look at these. We have 2 to the power of 3/4 times 2 to the, times 2 to the power of 7/8. Add the exponents, but these exponents are not going to add together so easy, are they? This is really going to be, I'll write it again like that, it's really going to be 2 to the power of 3/4 plus 7/8, right? Adding exponents. But now I don't have the same denominator for my fractions, so I have to convert the fractions. That's equal to 2 to the power of, well, let's fix this one to where it's 8ths. It's going to be, how many 8ths would it be? Well, I multiplied that 4 times 2, so I have to multiply the numerator times 2. It's 6/8 plus 7/8, right? And then I can add them together, and I end up with, I'm going to come over here. I didn't leave enough room to work on these problems, so I come over here and I say that's equal to 2 to the power of 6 plus 7, well, that's 13/8, right? Now, fix it so that it is a radical, okay? Go ahead and change it. It's going to be an 8th root, all right? It's going to have an index of 8, isn't it? And inside there, I'm going to have 2 to the power of 13. You just have to kind of memorize how that works, okay? So then I look at it and I go, okay, 13 is definitely bigger than 8. If I want to bring out the perfect 8th roots out of this thing, I'd look at it like this. I'd say 2 to the power of 8 times 2 to the power of what's left over? Well, 8 plus what is going to give me 13? 5. Yeah, I know. That's one of those I always mess up. I always can't get confused between 8 plus 5 and 8 plus 6. Never mind. All right, this one is a perfect 8th. When I bring it out, it'll be a 2. This one, there's nothing I can do about it because that index is smaller than, that exponent is smaller than my index. So then when I bring this out, it's 2 to the power of, that's the 8th root, whatever was left under the radical, 2 to the power of 5. okay? It's the worst page we have to do, people, okay? But you do have to practice at this. That's why my lab math has a lot of practice, and you go over those problems and do a similar exercise until you get proficient, okay? Yeah.
What happened if the two's in the front?
It really wasn't in the front. It was just a 2 with an exponent, okay? Okay, so when I changed it to 2 to the exponent of 13/8, it became a radical with an exponent of 13 and an index of 8. Does that make sense? Is that? I know. It's not the coefficient. This is not the coefficient. This is the exponent for the number 2. Okay? Let's take a look at this one. I'm literally dividing these two, right? And the way I do exponents, when I have division, same base with an exponent, I mean, I know they're fractions, but think about what you always do. Well, you subtract them, right? You subtract the exponent and you leave the remainder wherever you had the biggest exponent, don't you? Okay, so they're not the same denominator, but I can fix that. This could become y to the power of something over 8. Well, when I convert it, it's 2 over 8, right? 1/4 is the same as 2 over 8. And this is y to the power of 1 over 8. And now I can subtract exponents, can I? I can say, well, okay, I want 2 over 8 minus 1 over 8. That's going to leave me 1/8. So I'm going to have y to the 1/8. Where do I put it? Top or bottom? Top. So this really becomes y to the 1/8 over 1, which I don't have to write. So I can just kind of say, okay, it became a whole number. Now, write it with radical notation. It's got exponential notation. It's written as an exponent. Change it so that it's got radical notation. In other words, it is now the square root, or the root of y to the power of 1, but that index is an 8, isn't it? And then you look under that radical and you say, are there any 8ths? Are there any 8th roots? And no, it's just y, isn't it? And that's as simple as we get. And I realize how confusing this is. There's no way around this. We simply have to go through this, okay? You got a lot of time. You got a lot of math to do this week, probably. Okay, let's go to page 38. All right, now changing a little bit, I kind of backtracked. I did these not in the order necessarily that they are in my lab math, but it made more sense to introduce certain things to me before the others. So let's talk about division property, and that's really what we've just been working on, okay? It's the same as what we were working on before. The thing that you have to keep in mind with radicals is if you have a root of a, b, you can break it down into 2 radicals, right? And then we did that before. You can simplify it one way or another, and so we're just kind of have to work on that a little bit. What we have to remember here is that they're going to tell us, look at the word, to rationalize the denominator. Rationalizing the denominator, guys, means you can't have any roots. You can't have any radicals in there. So we're going to have to figure out a way. If we get stuck with a radical in the denominator, we're going to have to figure out a way to get rid of it, all right? And we have to figure out a way that makes that fraction, turns that fraction into something that does not have a radical, that root sign, in the denominator. So what I've got is the square root of 1/2, which is really the square root of 1 over the square root of 2, isn't it? So I rewrite it, just hoping it'll help me. But it really doesn't help me because I still can't get rid of that square root of 2 in the denominator. I'm already rid of the square root of 1. What's the square root of 1? 1. You see it? I mean, it doesn't matter. I could leave the radical in the numerator. It's okay. But I don't have to because this is really 1 over the square root of 2. So I'm going to come down here. I'm going to go, okay, this is really 1 over the square root of 2. But I still can't leave it like that. It has a radical in the denominator. To get rid of a square root, you multiply it by itself. Do you understand that? If I multiplied the square root of 2 times the square root of 2, I would simply get the number 2. Square root of 2 times the square root of 2 is 2. It's the same as saying take that square root and square it. What do you have? Well, you have the root. Okay? So that's how I get rid of, but now if I multiply a fraction, if I multiply the denominator by something, what do I have to multiply the numerator by? Exactly. So when I say 1 times the square root of 2, I have the square root of 2. And now for some of you, you're going, well, we're still stuck. We have a radical. It's okay. Radical in the numerator, it's fine. Radical in the denominator, they're going to say rationalize the denominator. Don't leave a radical down there, okay? Are you with me? Let's do another one. Let's take the square root of 64 over 81 and see if we can fix that so there's no radical in the denominator. Now, first thing you're going to do is you look at that fraction and say, well, will it reduce? Well, I see something about it that's pretty special. Both of those numbers are perfect squares. If you haven't memorized them, you're doing yourself a terrible disservice because you will not have time on the test to go through and try all the perfect squares, okay? You're going to have some things memorized. It's just the way math works. Okay? So perfect squares all the way up to 12. Put them on an index card and learn them. 1 squared, 2 squared, 3 squared, 4 squared, all the way to 12. You know most of them. All right, let's do this. What's the square root of 64?
80.
And what's the square root of 81? Now, we have gotten rid of all radicals, and we can look at this and say, will it reduce? Will 8 over 9 reduce? So no common factors, right? So we're done. Take a look at this one. Do the same thing to number 3. Find out what you can do to number 3. Split it into 2 radicals, and then see what happens. Okay. And like I said, memorize those perfect squares, right? Wouldn't hurt to go up to 13. But 12 you should know. 144, square root of 144 is 12, okay? And you knew 49. So if I look at that fraction, I go 12 over 7. That's not going to reduce. They don't have a common factor. So there, I'm stuck there, okay? All right, let's take the square root of 75 over 48. Now, these are not perfect squares, right? So I'm looking at other things I can do to them. First thing I'm going to do is split them into something over something, and I'm hoping I can find some perfect squares inside 25 and 40, and some inside 48 that I can get rid of. 75, you should kind of be used to this one by now. I see a perfect square in it, and I know it. 25 is the square root of 25 is 5. When I bring this out, it's going to be a 5, and all I'm going to have left under the radical is a 3. I'm going to go ahead and write that out here so I don't forget what I'm doing. 5 times the square root of 3. That's my numerator so far, right? 48. Well, I don't know if I see any perfect squares inside 48. So I come over here and I go, okay, I'm going to have to factor. 48, well, it divides by 4. 4 is a perfect square, so that's kind of a good one for me to divide by, and it goes to 12. And then 12 will divide by 4 and 3. Okay, I've got 2 perfect squares. You can do this any way you want to. You can take it all the way down to primes if you want to, but if you can find perfect squares inside it, then go ahead and find them. Because you know the square root of 4, don't you? When I pull this out, it would be a 2. And I got another 4, so pulling this one out, it'll make another 2. Now remember, to put those out front, I have to multiply them together. The 3, can't do anything with it, so it's going to stay. So what did this become? Well, this became 2 times 2, which is 4, times the square root of what? Well, the square root of 3, right? Now look at it. Now it's got a radical in the denominator, don't I? They're not going to let me leave it there. But look at it. This is 5 times the square root of 3, and this is 4 times the square root of 3. Anything over itself is the number what?
1.
1. X over x reduces to a 1. You know, pi over pi reduces to a 1. As long as it's all multiplication here, all multiplication there, I can reduce those. Square root of 3 over the square root of 3. It's like saying the square root of 3 divided by the square root of 3. Anything divided by itself is the number 1. And what I end up with is just plain old 5 over 4. Okay? Now, let's take a look at number 5. I'm going to have to move faster than I'm moving, so everybody wake up, okay? I know it's 8 o'clock. 6 over the square root of 10. They're not going to let me leave the square root of 10 down there, okay? What do I do to get rid of the square root of 10? Well, I can't simplify it. There are no perfect squares inside 10. If I factored it to 2 times 5, there's nothing that's a perfect square. So I've got to multiply it times itself. All right. So to get rid of that, I got to multiply it times itself. Therefore, I have to multiply this numerator by itself, right? By the same thing, I'm sorry. And then I end up with, okay, this is going to get rid of the radical in the denominator. And this is going to leave me with 6 times the square root of 10, which is fine. I already know the square root of 10 can't be broken down any further. But look, 6 over 10 can reduce, right? Remember, as long as it's all multiplication, in numerator and denominator, I can reduce anything. So this 6 can reduce with this 10. I would divide them both by the biggest number they'll divide by is 2. That becomes a 3. This becomes a 5. I will rewrite that as 3 times the square root of 10 over a 5. And that is its simplest form. And I did what they call rationalized the denominator. Look for the instructions you're going to be given. They're going to tell you to either rationalize the denominator, or you're going to tell you to write something in exponential notation, which means use exponents, or they're going to tell you to write it in radical notation, which means you're using the roots, right? The radical signs. All right, let's do another one. This one, look, inside that radical, I could reduce it now. I could go ahead and reduce it before I split it out, and that might be kind of handy. So let's see if I can't take 6 and 2 and divide them. This really becomes, and that's always a nice thing to check, this really becomes, they both divide by 2, this really becomes 3x over y. Okay, simplify before you break it out if you can. Now, I'm going to split this into 2 radicals. Sometimes with math, especially with algebra, you just do the next step. Okay, I can do that, right? I know how to split it. And then I look at it and say, well, now what would I do? Well, now I got to get rid of the square root of y, which is in the denominator. I got to rationalize the denominator. I've got to multiply it times itself. It's a square root. So if I multiply it times itself, I can get rid of it. It becomes just plain old y. Now in the numerator, everything that I'm multiplying, I can multiply anything under the same radical. These are all square roots, so I'm okay. And I say, what's going to be under that square root? Well, it's going to be 3 times x times y. Now that will not reduce, guys, because that numerator is not a y, it's a square root of y. And square root of y is not going to reduce with just a plain old y, okay? They're different. If it would have been outside of the radical, you could have reduced it, okay? Next, 1 over 15x. Are there any perfect squares inside 15? That would be my first thing. I would get the perfect squares out if I could. But do you see anything in 15? You'd come over here and you go, okay, well, 15, if I'm not sure, I factor it to primes. Nope, there are no duplicates there, right? So I'm stuck with 15, I'm stuck with x. The only way to get rid of it is to multiply it by itself. In the numerator, I'll have the square root of 15x. In the denominator, I'll just have 15x. Now, I already know that that 15 and that x are not going to, they have no perfect squares in them, so there's really nothing I can do at that point. Okay? All right, look at this next one. Will it reduce before we take it out from under the radical, before we split the radicals out? Will 2 over 35 reduce? Can we reduce that fraction? No. They're not. 35 is not an even number. It's not going to divide by 2. So the only thing I can do is split it into two separate radicals and see if I can fix it here. Are there any perfect squares inside 35? Well, I don't know. But if I factor it, it factors into two prime numbers, doesn't it? So it factors into 5 times 7. There's no perfect squares in 35. I'm stuck with the square root of 35. So if I'm stuck with that, then what do I multiply by to clear that denominator? Yeah, square root of 35, right? You're getting it. All right. Denominator. I got rid of the radical, didn't I? Numerator. Well, now these are both under the square root sign. They match, right? I couldn't do this if one of them was a square root and one of them was a cubed root, but now I can. I can multiply that 2 times 35. Well, 2 times 35, do you know what it is? 70. X. Don't forget the X, okay? Now you're looking at it and going, okay, I don't know. Are there any perfect squares in 70? Well, if you doubt it, if you don't know, if you're confused or you don't know, you come over here and you say, okay, I know it'll divide by 2, and I know this one will divide by 5 and 7. There's no perfect squares in it. You factor it to primes and check. It doesn't take long with your calculator if you're not certain. As it is, we're stuck with it, aren't we? Okay? All right, moving right along, page 39. How many pages do I have in this thing anyway? 40? 41? Oh, great. Okay. All right, let's talk about conjugates just a second. Now, conjugates are two terms, and I just wrote it up here for you. Guys, please take these blocks that are written at the top of your pages to heart. Learn what's in them, okay? If it means you have to write down terms and write down things on index cards that you're not familiar with until you got it memorized, then do that. But conjugates are really have two expressions, and so they're addition or subtraction between them, okay? They have the opposite center sign, okay? We don't care what the sign in front of this one is, as long as it's the same. That X and the X's have to match, the Y's have to match, but the operation between them has to be the opposite. If one's positive, the other has to be negative. So when I look at this one and they say write the conjugate, what they're trying to tell me to write is the same terms, opposite sign in between them. And why do we want to recognize conjugates? Does anybody know? Well, take a look at what happens when we multiply two conjugates, okay? We have to FOIL them, right? So we say first, 3 times 3 is 9. And then we say outside, well, that's 3 times negative 2. That's going to be a negative 6 to the, times the square root of 6. And then we multiply inside. That's going to be a positive 2 times 3, so that's going to be a positive 6 times the square root of 6. And then we do last. Well, that's a negative 2 times a negative 2 is going to be a negative 4. And then square root of 6 times the square root of 6 is going to just be 6, okay? But look what happened. Do you see these inside and outside terms? They're exactly the same but opposite sign. They're going to cancel each other out. Conjugates do that. You need to recognize conjugates, okay? Because it's going to make your life a lot easier when you're having to factor, okay? Recognize conjugates. So this is your job. Take those other 3 problems. You don't need nearly the space I gave you on this page. Take those other 3 problems and you write the conjugates. I don't even want you to multiply them out for me. I just want you to understand that's why we do it, okay? Okay, this one, the conjugate would be, we left that first term alone. The second term, we had to change the sign, okay? That's the conjugate. Down here with number 3, terms are the same, right? sign in the middle changes. Don't you wish it was all this easy? Right? I mean, this is simple, isn't it? Terms are the same. Sign in the middle changed. Okay? And you know why? If you multiply two conjugates together, when you do, it's a FOIL, inner and outer terms are going to cancel. Okay? So there's a shortcut to doing it, which we won't take time to get into today, okay? I mean, it's just simply you multiply the first and you multiply the last, and then you're done. All right, let's take a look at page 40. Maybe I'm ahead of myself. No, probably not. Okay, let's talk about complex numbers here, and this one might take me a little more time, because what I'm talking about is when I'm going to add the imaginary number in there. Now, the imaginary number is I, okay? Little I, cursive I, you know what I'm saying? That's the imaginary number. What does I represent? It is the square root of -1, okay? And we know square root of negative doesn't happen, right? Because nothing times itself is going to give us a negative. So we have pulled that out and given it a special name. It's called I, the square root of -1. Do you remember that from algebra years ago? Nope? Okay, well, here's a new thing. Square root of -1 is I, the imaginary number I. Now, another thing to memorize is right here. I squared is going to be -1. So when you have an I squared, you can just replace it with a -1. If you have the square root of a negative number, well, you're going to pull I out of it, because you can represent I all by itself, and then you can work with the number that's under the radical, okay? All right, let's take a look at this first example here. I've got 5 times the square root of -20, and normally we would have said, before this point in your algebraic life, you would have said, well, that can't be done. There's no such thing as the square root of a negative number. Guys, are you okay in the back? You have questions? You guys have questions? Okay. So I've got 5 times the square root of a negative, okay? So what do? Well, the first thing I do is think about it like this. This is really 5 times the square root of -1 times the square root of 20, right? And I know the square root of -1 is I. Now, I'm not done, but I got rid of the square root of negative, okay? That issue is settled. I'm just going to have to remember it as an I. Are you good with that? Good idea to write it as a cursive I, because you don't want to confuse it with any of our variables, right? X, Y's, H's, A's, B's. This is special. This is the cursive I. This is the square root of -1. It's the imaginary number. Okay? So now, let's take and see, can we simplify 20? Are there any perfect squares in 20? Anybody see one? Okay, you're saying 2 because you're saying 4 is the perfect square, and when you pull it out, it's a 2, right? He's right. So I got 5 times I. I'm writing it down for you like this, just in case you're not seeing it as quickly. There's my perfect square. When I pull that out from under the radical, it'll be a 2, and this thing has to stay. So let's rewrite it. Remember, everything that's out in front of this has to be multiplied times that term that I just pulled out. So I say 5 times 2. Well, that's 10. Don't forget I, right? What's left under the radicals of 5? So how did I simplify 5 times the square root of a -20? It's really 10I times the square root of 5. Yeah, ask me when you're going to use that in real life. I don't have your answer for you, okay? This is what we call critical thinking skills, people, okay? And I do know you will use critical thinking and problem solving for the rest of your life. So this is why I'm teaching you this, not because you're going to become engineers, all right? All right, let's look at this. Square root of -32x squared. Okay, first job, get rid of that negative. Square root of a negative has to come out. If you want to rewrite it as the square root of -1 times everything else, then do. But when you write that everything else, to save yourself some time, look for perfect squares inside 32x squared. Do you see any? What does 32 factor into? Did you say 4? So we got a 4, divide it by 4. Could you say that again? Yeah, that might be quicker, huh? 2 and 16. Oh, wait, there's my perfect square, right? You found that right away. Good. So I'll say, okay, I'm going to write that first. 16 times 2 times x squared, because look, x squared is a perfect square. I can pull this one out, and I can pull this one out. I'm taking the square root when I pull them out, right? All I have left is a 2, and this thing turns into an I, doesn't it? Okay, so I'm going to have to multiply all that together. I'm going to say, and always write the I last, all right? Just do your other variables and put the I last. So I'll say 4xi times what was left under the radical. That's it, just a 2. This is easier than what we did a minute ago, right? Yeah, we like this better than fractional exponents. I understand. All right, let's take and look at these two. Now, this is an interesting one. They both got square roots of negatives, right? So the first thing you do is pick them out. Now, if you're already to this point where you're okay, you can just say, well, that's really I times the square root of 12 times I times the square root of 6. Is that okay? I mean, do any of you see the need for me to rewrite the square root of -1 every time? Can I just put an I down? Are you okay? Not if you're okay. All right? Okay, if you're following along, that's good. If not, replay this part of the tape multiple times until you are, okay? So now I've got, well, okay, strange things. I can multiply those radicals together because they're both square roots. I can multiply the i's together because they're both the same. So I end up with I squared, don't I? Just like x times x is x squared, I times I is I squared. All right, then I say, okay, that's really going to be multiplied times, and I would say, all right, I'm going to multiply 12 times 6 together. 12 times 6. Well, maybe, yeah, okay. Did I say 12 times 6? Is that what I got? Huh. I never did this in my problem. But I think what I would probably do is try to break it down a little bit before I multiply. But go ahead, multiply 12 times 6 and start reducing. I mean, start breaking it down. Start looking for perfect squares. Might as well go ahead and simplify everything under the radical because you know how to do that, don't you? Now I've gone back. I did this a different way when I was working it last night myself. I looked for perfect squares before I multiplied them together, but then this morning I'm thinking that might be a little confusing. So I'm going back to what you know how to do, okay? So I'm looking at 72. All I did was multiply 12 times 6. I got 72. I don't know 72 really well, so I'm not sure of the perfect squares in there. Maybe you are. But anyway, I took 72 and I broke it down to primes. And I can see some perfect squares. I'm going to go ahead and say this is really the same as I squared times, and I'll just write the perfect squares first. 2 times 2 times 2 times 3 times 3. That's it, right? This is a perfect square. 2 times 2. 3 times 3, well, those are the same thing. Right? You good with that? What's left under the radical? Just the 2. So I say I have to multiply all these together. This is going to be 6i squared times the square root of 2. And now, this is where you figure out, oh, I squared, I remember that. I squared is equal to what? Go back to the top of the page. -1. So every time we see an I squared, we can say, replace it with a -1. This is 6 times -1. I already simplified the radical. This is really going to be -6 times the square root of 2. That's as simple as it gets, okay? Any questions so far on that? All we're doing is do what you know how to do. If I told you there were 10 ways to work that problem, there'd be somebody who'd find an 11th way. There are. You can go at it many different directions. Do what you know how to do, though, okay? And you know how to break down something under a radical into primes and find the roots, okay? You know how to do that. All right, let's take this one over here. Ugh, this one is a rationalize the denominator problem, isn't it? Don't I really have to do something about that square root of 6 down there? I'm not going to be able to leave it. But I've also got to do something about this negative, square root of a negative. So it depends on what do you want to do first, right? So I think the best shot or the best chance you have of not making mistakes is to get rid of the square root of -1. Get it out before you do any more math, okay? So let's change this to I times the square root of 25 over the square root of 6. All right, is everybody okay with that? All right, what's the square root of 25? 5. So this is I times 5. Well, we always write the I last, don't we? This is 5I. Now, we know we can't leave it like that. You don't have any perfect squares inside 6, so it's as simple as it gets. What do you do to rationalize the denominator? Exactly. Exactly right. And now, in the denominator, I have just a 6. In the numerator, I've got a really strange looking thing that I don't know what to write first and what to write second, right? So usually what we do is write the I last. We'll go 5 times the square root of 6 times I. Okay, make sure the I is not under the radical, okay? When you put it into my lab math or you put it in there, you're giving your answers like that I can't go under that radical sign. That's why I put a little ending point to the radicals so that you'll know that's where it ends. It just helps me. Are you good? We're not doing anything different now. We're just doing the same thing. We just do it in different orders, and we just do what we know to do next. All right, take a look. Usually we write I last, so that's why I did it. I mean, it could have been 5I times the square root of 6. That would have been okay, but I just chose that. And I don't think I don't think my lab math would even give you any trouble if you wrote it the other way. But let me know, because I'll be interested to find out. All right, let's look at this one. I've got 12 plus the square root of -20 over 5. And now what I want you to do is to get rid of that square root of negative deal. But when you start looking at what can you do after that, pay attention. This is not multiplication up here. This is addition. So you can't reduce everything, all right? I mean, this is addition. This is different. So get rid of the negative. Get the negative out from under the radical first. And then see if you can reduce that square root of 20, which is what you're going to have to do. See if you can get something else out when you do that. You should see it. I'm going to go back and reverse what I just said. Let's write it like this, because I have a note to myself that this is what my lab math likes. Okay? Put your I in front of your radicals. It'll be okay. It'll be okay either way. Okay, that's what I got when I took I out. And now I'm going to take the perfect squares out of 20, okay? Don't forget, all that work I'm doing in the numerator, the denominator is still a 5, isn't it? So what do I have? I have 12 plus 2I times the square root of 5, and it's all over a denominator of 5. Now, listen, when there's addition or subtraction involved in either your numerator or your denominator, you cannot reduce everything, okay? You can't reduce at will. What we were doing with reducing things, numerator, denominator, is when every term, every item is being multiplied, when it's really one term in the top one and one term in the bottom. Remember, terms are defined as they're stuck together with addition. Stuck together with multiplication. There's no addition or subtraction. If there's addition or subtraction, you cannot reduce at will, okay? You can't reduce one with one. Everything would have to have common. Now, I look at it and I go, okay, to be able to reduce these three numbers, I'd have to reduce all three of them because there's addition stuck there, and I can't. And the square root of 5 is not the same as 5 anyway, right? So that's really my answer. Are you good? Did you get that one? All right, let's see what we can do with this next one. Go ahead and take out the square root of the negative 1. This one is pretty simple. And it shouldn't take you long. Here's my solution when you're ready for it, okay? Any questions on that? You should have seen, or you probably saw pretty quick, the square root of 36 is just 6. And then when I have these terms together, that subtraction up in the numerator keeps me from reducing, doesn't it? Okay? They would all have to have a common factor before I could reduce them. Okay? All right, let's go on. Last page. All right, how do we add and subtract complex numbers? Well, this is not multiplying and dividing two terms. Okay, this is not multiplication of two terms. This is adding two terms together and subtracting two terms. Note that there's a plus sign between these binomials. Do you see it? So now when there's a plus sign between them, nothing changes. The signs inside the parentheses don't change. So you really rewrite it like this. Just get rid of the parentheses, okay? Because what are you doing? You're really distributing a -1 times those two, a +1 times those two terms. It doesn't change anything. So I can, there's a plus, when I'm adding two binomials together, all I do is get rid of the parentheses. And then I combine like terms. Well, what's alike? Well, this 3 and this 4 are alike, so I can say 3 plus 4 is 7. And then the I terms are alike, aren't they? I've got 2I and a -3I. How many I do I have? Yeah, -1I or just -I. And that's really all. There's nothing else I can do to that one. Now, notice the difference in example 1 and example 2. Look, do you see the negative? We can't just take away the parentheses, okay? You take away the parentheses from the first one, the first binomial, because we're not distributing, but we are distributing a -1 to each of those two terms. If you need to remind yourself of that, then definitely draw the arrows. So what do? I say negative times 4. Negative 1 times 4. Well, that's a negative 4. Negative 1 times negative 3i. That's a positive 3i. In essence, what happens when you have a negative outside parentheses is it changes the sign of everything inside. Okay? This was a positive 4, it became a negative 4. This was a negative 3i, it became a positive 3i. Now you get to combine like terms. I have a positive 3. I have a negative 4. Remember, when you're circling them or putting blocks around them, include the sign that's in front of the term. So this is 3 minus 4. This is a positive 2i and a positive 3i, which is a positive 5i. It's a negative 1 plus 5i. Are you good with that? So we just combined two binomials, adding them, subtracting them. Subtracting them is where you get into trouble, so pay attention to that one, okay? Now let's multiply. I'm going to say this term multiplied times a binomial. Well, remember, I have to multiply it times each term inside parentheses, right? So I say 2i times 2. Well, that's 4i. And I say 2i times a negative 7i. Well, I'm going to just multiply those first, those coefficients first. I'm going to say 2 times negative 7 is a negative 14. I times I is I squared, isn't it? All right, every time you have an I squared, you replace it with what? Negative 1. So what we really have is 4i minus 14 times negative 1, right? Because that I squared is being multiplied times that negative 14. What do you have now? Well, 4i plus 14, right? Take a negative 14 times a negative 1 becomes a positive 14. Are you good? Do this next one. This was not hard. There's no I squared in this thing. Go ahead and just distribute the multiplication. It should be really fast by now. You get it? You should be really quick on those because that was an easy part. One step. All right, down to FOIL, right? Now foiling, before we were saying foiling conjugates gets rid of the middle too, and that's why we like to recognize it. But these are not conjugates, are they? So what I'm going to do is first outside, inside, and last, and then I'm going to combine like terms, and I'm going to look for some funky stuff to happen to me because there are i's involved. I'm going to end up with some I squares, okay? So let's do it. I'm going to go over here and write it out for you one time. FOIL, first, I'm going to multiply first terms together. 3 times 5, 15. And then the next one, outside. Well, these outside terms are 3 times negative 3i, aren't they? That gives me a negative 9i. Inside terms, well, that's right here. 2i times 5, well, that's going to give me a positive 10i. Don't forget, the signs have to go in there because they're separating the terms, aren't they? And then last terms, 2i times negative 3. Well, let me put the last there. Last terms, 2i times negative 3i is going to give me a negative 6i squared. Okay, now I'll start working on combining these terms that are alike. Well, really what I see right away is this. You know? And then I see this. This is really negative 6 times negative 1, isn't it? Right? So if I need to, I go out here and I say, well, replace this by negative 6 times negative 1. I'll write it out like that. Scratch it out if I want to. What I've got is 15, and when I combine a negative 9i and a positive 10i, I just get a positive 1i. So that's plus I. And I have a negative 6 times a negative 1, positive 6. Still not done. Still got like terms to combine. What do I have? Well, I have 15 and 6 now, don't I? 15 plus 6 is, thank you, plus I. It's just extra steps in there because for some of you, you want to write that down a whole nother time. It's because you're going to be multiplying times a -1. If you can't do that in your head, then write it down. All right, FOIL this second one for me, okay? Go at it. See what you can do with it, and then I'll take it and write it out for you. The negatives are the hard part, so don't lose a negative when you're doing this multiplication. Okay, first terms, -1 times 3, -3. Outside terms, -1 times -3i, +3i. Inside terms, I times 3, another +3i. And last terms, I times a -3i, well, that's going to give me a -3i squared. So inside terms that match, and they do, so that's okay. And over here I'm going to say -3 times -1. Now let's kind of get all of that written down. I've really got -3 plus 6i plus 3. Did you get it that far? You good? Okay, so you look at these and you go, well, -3 plus 3. It's same as saying 3 minus 3, isn't it? Isn't that 0? I don't have to write 0. I don't ever have to write plus a 0, do I? So you should have gotten 6i. Did you get 6i? Yay. Okay, good. You're going to ace the test then, guys, okay? We need to ace this next test. Come on, we need to ace this next test. All right, so what do we do when it says square the thing? How are you going to do that? Exactly. So you can't just square each term, right? You have to rewrite the thing. Square root of 3 plus 6i times the square root of 3 plus 6i. Are these conjugates of each other? It's not a trick question. No, it's not, right? So there are going to be inside terms that don't cancel each other out. Conjugates would, but this is not a conjugate. So I'm going to square by multiplying by FOILing. Okay, go ahead and do that one. Remember, the square root of 3 times the square root of 3 is what? 3. Okay, good. Okay, square root of 3 times the square root of 3, that's just 3. And then I'm going to go outside terms. Square root of 3 times 6i. Well, that's going to be plus 6i times the square root of 3, right? And inside terms, square root of 3 times 6i is another 6i times the square root of 3. And last terms, well, that's going to be 6 times 6, I times I. Okay? What can we combine? Well, now listen, when you talk about combining terms, everything after that coefficient of 6 has to be the same. These are I square root of 3's. These are I square root of 3. So I can add them together and say 6 plus 6 is 12. 12 what? I times the square root of 3's, right? Do you see that? Everything after that coefficient, the numeric coefficient matches, then you can add them or subtract them. And then this is really plus 36 times a negative 1, which is minus 36, isn't it? Okay, so let's do that. 3 minus 36 is going to give me a negative 33. And what do I do with 12i times the square root of 3? Well, if I could find a square root under there to get it out, but there's no such thing as simplifying a square root of 3, is there? So I'm done. Yes? Yeah, I'm kind of going to reverse what I said before. We're going to put it in front of the radical, okay? We're going to say coefficient, and then the I, and then the radical, because it'll be so much easier for you to simplify, add them together when you see that, okay? Okay, last one. You should be able to do this one. Go ahead. Some of you have already gone ahead, haven't you? Okay. Did you guys see there's a hurricane out there? Not right now, but I mean, Sam, I think it is. Have you seen where it is lately? Okay. Yay. I mean, it's almost October. It hardly seems fair to get hit by one in October. That's true. All right, I'm going to FOIL this one. I'm going to say 4i times 4i. I'm going to multiply those first terms together, and I'm going to get a 16i squared. I multiply the outside terms together. I'm going to say 4i times 6, and that gives me 24i. Inside terms, 6 times 4i, another 24i. And last terms, 6 times 6, positive 36. These are the same, and this is 16 times negative 1, right? 16 times negative 1, negative 16. And then I'm going to add together these i's, and I get 48 of them, plus 36. Okay. Then I can combine these. Really, it's the same thing as saying 36 minus 16, isn't it? So that gives me 20 plus 48i. I don't think I can do anything else to that. You guys good? Okay, now I've got a minute, so I'm going back to your conjugate page. Don't leave me yet. Go back to page 39. And I want to give you just a tad of practice, okay, with 39. I want you to take these conjugates that you created, and now I want you to multiply them by each other. In other words, I want you to take -3 minus 2 times the square root of 6 and multiply it times -3 plus 2 times the square root of 6. Remember, inside and outside terms with conjugates are going to cancel each other out. Try it with this one, but then see if you see the shortcut, okay? Are you good? Okay. When I did first terms, I said -3 times -3 is +9. Then I did outside terms. I said -3 times 2 times the square root of 6 is going to give me -6 square root of 6. Then I do inside. -2 times -3 gave me a +6 square root of 6's. And then I did last terms. -2 times +2, that's going to be a -4. When I multiply the square root of 6 times the square root of 6, I just get 6, okay? What happened to my inside and outside terms? They do. One of them's a -6 square root of 6, the other one's a +6 square root of 6's. When I combine those, add them together, they're nothing. So really I have 9 minus 24. What's 9 minus 24, somebody? Right? Now, do you see the shortcut? Somebody tell me, what would you, in your own words, how would you shortcut them if you're multiplying conjugates? What can you do?
Multiply the first terms of each one.
Okay, so you multiply the first terms. So I would multiply -3 times -3 is multiply the last terms, and that's it. Conjugates, inside and outside, will cancel each other out. But they have to be conjugates, so you have to recognize conjugates, right? Now go back up here to where this says the terms are the same with the exception of the signs. And the sign I'm talking about is the sign between the terms, okay? Not the sign in front of the term. It has to be the sign between the terms. It has to be different. Everything else is the same. Let's do this one more right here. Do example 3. Use your shortcut, okay? Okay, this one's simple, isn't it? So what did you get, somebody? I multiplied 6 times 6, and I get what?
36.
And I multiplied last terms, negative square root of 5x times positive square root of 5x, what am I going to get? You see it? This is a negative 1 times a positive 1, isn't it? That's how I got the negative. And square root of 5x times square root of 5x, I got rid of the radical. So really, what have I got? 36 minus 5x. Do you understand? It's a shortcut for conjugates. If you have conjugates, then you can shortcut it. That's the only time you get to shortcut that, okay? All right, guys, you got a lot of work to do. I will be in office hours. What's today? Monday? I'll be in virtual office hours Tuesday evening. If you need help, come in there between 5:30 and 8. Send me problems if you have them ahead of time or at another time, and I'll help you. Now, we'll see you Wednesday.